Welcome back. In this video, we are going to be looking at Mason's gain rule. Now, Mason's gain rule is one of the most common and popular shortcuts in finding the transfer function of any control system. So, in our previous videos, we've discussed about using the meaning of nodes, forward path, backward path, feedback path, and different terms that are associated with our signal flow graph. But in this video, we are going to be going straight into how to make use of Mason's gain rule. So here is the formula of the Mason gain rule. This is Mason gain's formula. It's simply the transfer function is equal to the sum of pk, change in k, or determinant k, divided by the determinant. What does this mean? So I'm going to be making use of this diagram to illustrate what each of these terms simply mean. So the first one is the transfer function. What is the transfer function? The transfer function is simply the ratio of the output to the input. In this diagram, we have an output signal. The output signal is C, while the input signal is R. So the transfer function, which is what we are actually looking for, is the ratio of the output signal of C to the input signal. Now, what is this determinant? Before we go to the determinant, let me explain what K is. K is simply the number of forward paths. A forward path starts from the input and takes you to the output. So how many forward paths can you identify from this diagram? If you look at it carefully, you can see that we have one forward path, which is the main forward path. It starts from here, and by the arrow you can see that it is going down to the output. That is one forward path. Then another forward path you can see is this. Starts from here, it climbs up and it goes to the output. Remember that forward path is starting from the input and takes you to the output. Now, is this a forward path? No. First of all, it's not even starting from the input, and it is not going forward. You can see that it moves from here and returns back by the arrow, so it's not a forward path. Same thing applies to this one. It's going back. It is not a forward path. The forward path moves from the input to the output. So for this problem, how many forward paths can we say we have? We only have two forward paths. One from this point to this point. You start from here to here, and another one from here to here. By the arrow, you will know that is a forward path. So we have two forward paths. So the next thing we should know is this determinant. Determinant is simply 1 minus sum of all individual loop gain. What is a loop? From this diagram, the loop is simply we start from a node and returns back to that same node. Look at this start, it moves from this point, went to this point and came back to this point. Then is a loop. Also, it starts from here, another loop again, it starts from here, went to node 4 and came back. So that is a loop. So these are all loops in this problem. So it is 1 minus sum of individual loop gain plus sum of the product of two non-touching loops. What are non-touching loops? Non-touching loops are two loops that don't share a common node. Remember, we've identified two loops in this particular question. For now, this is a loop and this is also a loop. This bigger one is also a loop. So do they share a common node? Yes. The bigger loop, which is from 1 to 4, inside 1 to 4 we have node 2 and 3. So it's sharing the same node. So that is not, these two loops are not, they are not under this category. Remember that this one is saying that the product of two non-touching loops. These particular loops are touching, so we can't include it. When we get there, when we start solving problems, applying the formula to be able to see what we are talking about. Then we go on. Then PK is the gain of the kth forward path. So for example, like we said that we have two forward paths, the one that starts from here and end at this point. So the PK is simply the gain that I can identify on that particular path. That is PK. Then we have change in K. This determinant K is simply same thing with what you had here. But in this case, we are going to be considering the one that is not touching that path. So without wasting much time, let's go in straight into applying this formula to this particular problem. So let's do. So see, applying the Mason's gain is equal to the sum of Pk times change in K divided by delta. So you ask yourself, the first thing you need to do is identify how many forward paths we have. We've already established that we just have two forward paths. So this formula is equal to P1 change in 1 plus P2 change in 2 divided by our determinant. It's no more a general term now because we've seen how many forward paths we have. If we have more than 2, we will still add plus P3 and determinant 3 in this place. So we'll be working with this. Now the first thing we need to do is let us find the P1 and P2. That is the forward path gain. So our P1 is equal to what? Remember our P1 starts from what? It starts from 1, goes to 2, goes to 3, goes to 4. So our P1, which is the main forward path, it starts from this node and takes us to the last node. That is our P1. So this P1 is simply the gain. So what is the gain in this node or this path that we have talked about? The gain is simply what is resting on this branch or this path. So what is resting on this path is G1 times G2 times 1. So we have G1 times G2. That is P1. So let's do the same thing for P2. What is our P2 path? Our P2 path starts from node 1 and takes us to what? Node 4 before going to the output. So it starts from node 1 and takes us to node 4. So let's identify the gain in that path. So the gain is simply what? It starts from here and moves to this point. So the gain is just G3. So the gain for this path it is just G3. So now we've identified P1 and P2. Let's go into the determinant. Let's find the determinant. So to find the determinant, we need to first find individual loops. Or let's put it this way. The sum, let's use it as individual loops. Let's get the individual loops. So looking at this problem, we have how many loops? We've already said that loop 1 is what? It starts from this node, goes to this node and return back. So that is a loop. So can you identify the loop gain? We want to write the individual loop gain. What is the loop gain here? So the loop gain here for this first one is what? Minus G2H1. It's just to multiply all the gains. The gain here is G2, the gain here is H1. So you multiply all the gain in that loop. Which other loop can we see? We have another loop. It starts from here, goes to here, and return back to that node. Remember that's the meaning of a loop. So that is another loop, L2. And what is the gain? Is G1, G2 times 1, then times minus H2. So I'm supposed to have a minus here, then H2. Remember, we are trying to get all the gains that is on that loop. We've said that the loop is from here and take us down to this point. So all the gain on that loop is this, and this. Is there any other loop that we can find? Yes. One more loop. If you look closely, you can see that there's another loop that starts from here, moves to this point, and return back. So that is a loop. So L3 will give me what? What is the gain of that loop? G3 and what? Minus H2. So we have minus G3 and H2. So we've identified all the individual loops that we can find in this question. So the next thing we need to do now is to get the non-touching loops. Let's look closely if we can find the which is individual loops. Let's get the non-touching loops. So what are the non-touching loops? Remember we said that non-touching loops, they don't share common nodes. Now these two loops that we talked about, is there any of them that is not touching? Right? This is loop 1 and this is what? Loop 2. So you can see that in loop 2 and loop 1 they are sharing a common node. This is loop 2, it starts from here, takes all these nodes and goes here. Loop 1 is what? 2 to 3. So you can see that they are sharing nodes together. What about this other one, the last loop? So this last loop is starting from 1 and 4 alone. So you can see that this last loop that we talked about is not sharing any node with this one that is inside because it is just from 1 takes straight to 4. It doesn't pass through this middle. That is the last loop. So we have two non-touching loops, L3, which is L3, Or you can say, let's use L1 and L3. So L1, which is this bigger one, is not touching this one that is inside because it just starts from here and went straight to 4. Then this is this. So they don't have any, you're not sharing any common loop. So we have L1 and L3. So what is the gain of those two loops? That's what we want to look at. So the gain, we have to take the general gain, the product of these two loops. So it is simply what? Loop 1 and loop 3. If you multiply them together, what do you have? You're going to have G2, G3, H1, and H2. So what about this loop, this L3, right? What about this L3 and L2? So you can see that L3 is this one that starts from here to here and went back. And L3 is this bigger one. You can see that both of them are sharing nodes, 1 and 4. So we are not going to include that. We only pick the ones that don't have any common nodes, which is L1 and L3. So let's go on. So we've identified the non-touching loops, two non-touching loops. Is there any three non-touching loops? There's no three non-touching loops, so we stop here. Now let's go to change the one, and remember that I'm trying to get all this that is here. So we've gotten P1, we've gotten P2. Let's get the determinant 1 and determinant 2. So for determinant 1, is simply 1 minus from the question, from the what we are missing here is the part of this determinant that is not touching the forward part. So since I'm at P1, I'm trying to get 1 minus the loop that is not touching this P1. Look at our P1, start from here and went to here. Is there any loop that is not touching that part? All the loops that we have discussed so far, all of them, they have a node on this particular part. So there's no loop that is not touching. So because there's no loop that is not touching, we put a 0. So 1 minus 0 is 1. So this is the main forward part from this point to this point. You are not asking yourself, is there any loop that is not touching this long part that starts from here to here? It's not possible because all the nodes, all the loops are attached in one way or the other to this main forward part, this P1. All of them are attached to it in one way or the other. So let's go to P2. So for me to get this determinant 2, it is the same process. Ask yourself, is there any loop that is not touching this part? What is the part? The part is from 1 to 4. So from 1 to 4, is there any loop that is not touching it? Yes, because from 1 to 4, 1 straight to 4, this loop is not touching that part. Remember, look at the path. See where it's following. From here, it flies up to this point. Is there any loop that is not going the same direction? Yes, this one is not among that side. It's not in that area. So this one is not touching this part. So we have to sum the loop. Okay, and it's only one. So we just take this one, the loop gain. So the loop gain is what? Minus G2 H1. So when you do that, your chain A2 is now 1 plus G2 H1. Okay, now we've gotten everything we need. Let's substitute it back into this transfer function formula. So my transfer function formula, I want to substitute it now. So where will I do that? Let me do it under here. So transfer function is equal to what? P1 changing 1 plus P2 changing 2 divided by determinant. So my transfer function is equal to what's my P1? The P1 gain is G1 G2. So G1 G2. What is my determinant 1? My determinant 1 is what? 1. So times 1 plus P2. What is my P2? My P2 is G3. What is changing? So my changing 2 is this. So I'll put a bracket 1 plus G2 H1 divided by what is this determinant? Remember we said here, see the formula here, the general formula. So we are going to apply it. So it is simply 1 minus, I will open my bracket, the sum of all the individual loop gain. See the individual loop gain that we're able to get. So we are going to add them together. That is what? The first one is minus G2 H1 followed by minus G1 G2 H2 and lastly minus D3 H2. So this is all the loop gains, individual loop gains. The next one is what? We should add it with the sum of the product of two non-touching loops. So plus the sum of the product of two non-touching loops. How many non-touching loops do we have? Just this one. So we are going to plus it with this. G2, G3, H1, H2. So if I open the bracket, what I'm going to have finally as my transfer function is equal to G1, G2 plus G3 bracket 1 plus G2 H1 divided by 1 plus G2H1 plus G1 G2H2 minus G3H2 plus G2 G3 H1 H2. So that is all using our transfer function of Mason's game to find the transfer function. So this is simply how you're going to be using Mason's game to find the transfer function. And we've come to the end of the video. Please, if you've learned something, do well to subscribe, share, and leave a comment if there's any part of this that you are confused. And I will meet you at the comment section. Thank you, and see you in our next video.